Looking at electron configurations, you may have seen or felt like over the span of doing a number of examples that there was a lot of redundancy there, that you were writing the same thing over and over again. So you might have wanted a shorthand way. By the same token, what we see is that of that whole electron configuration, very little of it has any impact on how the element will react. It's only the outer ones that we're really concerned about. So to that extent, we end up with the shorthand method that we call the inert gas configuration. So as we mentioned, we're most interested in the outermost electrons, and that's because those electrons are the ones that are giving your reactivity of the element. So to emphasize this point, the inner electrons are often replaced with the inert gas that ends in the energy level before the element. So I like to say that you have to look for the noble gas that you've passed. If you're looking for the noble gas itself, again, you have to go back to the noble gas before it, the next noble gas you've passed. So for example, if we look at sodium, which is Na, and it has 11 electrons, its electron configuration looks like this. It's a 1s2, 2s2, 2p6, 3s1. Now, if that whole thing is just this one outermost 3s1 electron that contributes to its reactivity. So the question is, well, what noble gas does this portion represent? Because we know the noble gases don't ever change their electrons. They're very unreactive, and they very rarely will share or change their electrons. So we can use them as a constant. So what we see is that we have there 10 electrons. 2 plus 2 plus 6. So 10 electrons. The noble gas with 10 electrons is neon. And we have to put square brackets around it to say that, or to show that it would be all the electrons that neon has, which is 10, and the 3s1. If you were doing this quickly, you could look at it and go, okay, well, I'm starting at sodium. What's the nearest noble gas I've passed? The one before it. That happens to be neon. I've got 1 electron left. When I look at neon, it's got 10 electrons, so I count up 10 on my energy level diagram and go to the next possible orbital, which happens to be the 3s1. I'm going to ask you to do quite a bit of practice with this next day. Also, I need you to remember that when we look at ions, ions have charges. Atoms are neutral, which means that the number of electrons is the same as the number of protons, so it has the atomic number. Ions are charged, meaning that the number of electrons is the number of protons minus the charge. There are extra negatives if you have a negative charge on the ion, so that means you add the number of electrons. If you have a positive charge, you have to take those electrons away. So looking at the electron configuration of iron, iron having 26, 1, 2, 3, 4, 5, 6, has 26 electrons for the atom because that's the same as the number of protons. So placing them in, I know that I go 1s2, 2s2, 2p6, giving me 10, 3s2, 3p6, giving me 18. Now this is where we have to skip to the 4s because it's actually the next lowest energy, even though it's farther from the nucleus. 2, and then I go back and fill the 3d, and I need to add 6 more electrons. Now, when I look at the electron configuration for the iron ion, that's a 3 plus, it has 3 more positives than negatives, which means that I'm looking to place 23 electrons. Now the common mistake here is that people will just start out from scratch and go, okay, well I have 23 electrons. Instead, what you have to do is consider that when you steal electrons, you steal them from the outside. So I'm just going to quickly rewrite the electron configuration for the atom. 3s2, 3p6, 3d6, and 4s2. So these 4s electrons are the furthest ones from the nucleus. So even though they weren't the last ones I added, they're the first ones I cut off. So that's 2 electrons that come off. And I need one more electron to go. So that means I need to change this to a 5. See how we fill the electrons in terms of energy level, but we take them off in terms of distance. And that's really why I asked you to order them so that all the same principal quantum numbers, which really represent a distance, are grouped together. The other thing I can talk about is the fact that there are some electron configurations which are the same. And that brings up a term which means isoelectronic. So iso means the same, and electron means electron configuration, just like you would assume it does. So this means isoelectronics means having the same number of electrons and the same electron configuration, but not the same number of protons and the same properties. It's not the same element, it's not the same ion. It can be an ion of one thing and an ion of something different, but it's not of the same element. Most elements want to become isoelectronic with the nearest noble gas or inert gas, and that's because we know that those things are exceptionally stable, and that's why they will gain or lose electrons in order to do so. So magnesium as an atom is 1s2, 2s2, 2p6, 3s2. Notice these 3s2 electrons are not part of a complete energy level. So to become its ion, it loses those 2 electrons and becomes a 2+ ion. In the same way, now this has 10 electrons. It is now isoelectronic with neon because it has the same number of electrons, the same electron configuration as neon does. So the next thing we need to go over again is a ground state versus an excited state. So all of the electron configurations that we've done for elements are in their lowest energy state, their ground state. We fill them as if we would follow the energy level diagram. When electrons, though, gain just the right amount of energy, they can jump to a higher energy level. But they want to be in the lowest energy state possible. So they lose that gained energy by jumping back down. Remember, this is how we get our bright line spectrum. And remember that the different wavelengths of radiation represent different photons of different energy, so the color of the light emitted by an element depends on the energy gap between the sublevels. Anytime you see elements filled in the order you would anticipate based on the energy level diagram, 1s2, 2s2, 2p6, 3s1, that represents a ground state in the most relaxed state. Anytime you have them placed outside of that order, that represents an excited state. There are ones that people will write in to try and trick you where you have, for example, a 3s3. That's not an excited state. That's impossible. We know that orbitals can have a maximum of 2 electrons in them. But any order that you filled it that's possible but isn't in the order you would expect represents an excited state. The last thing we need to talk about for this particular topic is orbital stability. And what we see is that most stable orbitals are the ones that are either completely full, so that they have all paired electrons, or are half full. So there's no paired electrons, because we know electrons are negative and they don't like to be together. These types of orbital are lower in energy than those which are partially filled, even lower than we would anticipate they would be. And this is particularly important when we look at p, d, and f orbitals. Sometimes what we see is that atoms will rearrange their electrons between the orbitals close in energy level in order to obtain one of those conditions. You may have seen that the 3d and the 4s are actually very close in energy. It's actually hard on some versions of the energy level diagram to read it properly because they seem to be so close. So the transition metals, which have their d orbitals being the last ones full, will lose electrons from their outer orbitals, and the d orbitals form stable ions. And for lots of these, they can form ions that are stable in more than one way, and that's why we get multivalent ions. So this ends all the new content for our discussion. So this ends all our new content for our discussion of electron configurations. We're going to do a lot more practice next day, as well as a lab which is based on this.